Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we're very happy to have Eitan Bakmat talking today from Ben-Gurion University, and he'll be telling us about numbers and queues.
Thank you very much for the invitation. Okay, so I'll make some observations on the relations between number theory and queuing theory, and we'll do it through a very simple-minded example. Okay, so really nothing fancy. We're going to look at a mini market. So a mini market will have two counters. This is counter number 1, and here's another counter, which is counter number 2. Okay, so we have these two checkout counters, and people arrive here to the counters and where they want to check out. And what we're going to look at is a very particular type of queue management, which involves sort of the idea of an express line. So what's the idea in an express line? The idea in an express line is that you consider some cutoff, let's say S. Usually, I don't know what the situation is exactly now in the US, but the idea is that usually it's by the number of items. So you would have, if you have more than S items, you go over here. If you have less than S items, you go over here. But items is a pretty murky thing because it turns out that it's not too well correlated to the amount of time you're actually going to spend at the counter. And what we actually want is, suppose we had a sort of like an oracle that could tell us exactly how much time you're going to spend at the counter. So S is going to be a cutoff expressed in terms of time. And if you take less than S time to process, you're going to be navigated to the express line, to line number 1. Okay? And if you take more than S time to process, I'll navigate you to line number 2. Okay? It's not the only thing that could happen. You can choose the shortest queue. You can do something else, but let's stick to some really simple stuff. So we'll do it this way. Okay, so we have this simple queue. And now, in order to turn this into a mathematical problem, I still have to give you some information. So one of the things that I have to give you is, what is the arrival process? How do customers arrive at the queue? Okay? And again, we're going to try to keep it simple. We don't want to confuse ourselves. Let's go for Poisson process, okay? So Poisson process essentially means that customer arrivals are independent of each other, and the time between two customers is exponentially distributed. In another way you can think about it is, it doesn't matter how much time passed since the last customer arrived, you don't have any information about the arrival time of the next customer. So this, we're going to take the simplest possible choice. Otherwise, you usually can't really write down explicit equations. So, and we're going to have some rate. Well, the customers arrive, I don't know, 3 customers a minute, or something like that. So this is one thing I have to specify. The other thing that I have to specify, and this is really important for determining the cutoff, is what is the distribution of time spent at the counters, okay? For example, if everybody takes more than 10 minutes and my cutoff is 5 minutes, it's not going to do a good job. So I have to give the distribution of service time at the counters. And let's call that x. Let's call this distribution x. Okay? There's another thing that's important for determining the cutoff is what is my optimization problem? What am I trying to optimize? Okay? Again, we're going to go for the most standard choice, which is minimize the average time for waiting. So W will denote the waiting time of a customer in the system, and we'll just average over all customers and try to minimize that. We can make other choices, and I'll talk a little bit about other choices later. Okay? Now, okay, so these are the basics. Once I give you all these, and I choose a cutoff, I can actually determine mathematically the waiting time and try to optimize. Okay? Now we're going to add a little twist, something a little bit, which is actually realistic. In a mini market, you don't only have counters. Again, unless if you're in one of these self-checkouts, you also have people manning the counters. And obviously, these will be Alice and Bob. Usually they exchange bits every day, but today they're going to man the counters instead. Okay, so, and this is the setup. Now, Alice and Bob are not necessarily equally capable workers. But again, we're going to take the simplest possible model that can differentiate between them. And this is the uniform speedup. So what does uniform speedup mean? It means that if it takes Alice t time to process a job, it takes Bob a constant time c for all the jobs, the same constant for all the jobs. Okay, so Alice is 4 times faster than Bob on every job, or 2 times slower. Okay, and obviously for symmetry reasons, we can restrict to say c greater than 1 or something like that. So
when you said you wanted to minimize expected waiting time, what do you get to vary here? Like the cutoff? Or?
The cutoff, yeah.
Okay.
I get to vary the cutoff. This is my
Right.
single dimension
Good.
optimization
Good.
problem.
Good.
How difficult can that be?
Good.
Okay, so this is so we have a uniform speed. So our
But you already fixed the distribution of service time.
so we'll do it with respect to Alice. This x is always with respect to Alice. Okay?
C is a parameter.
And C, yeah, speed up parameter. Okay, so I've specified my system, and now I can ask managerial questions. Sloan School is not far away. Let's try to pretend to be mini market managers for the day. So, question number 1. Let's assume that C equals 1. Well, let's assume they're equally capable workers. What is the optimal cutoff S? And this would be a function of, well, could be in principle of the arrival rate and also, and definitely, of the job size distribution. Okay? So that's question number 1. Okay, question number 2. One second. Okay, yeah. Suppose C is greater than 1. Alice is faster than Bob. Okay? Where should I place Alice? Should Alice be working the express line? Or should she be working the, the slow job line? Now, it could make a difference. What do I mean by this question? I place Alice in the express line. I optimize over all possible cutoffs. I get a certain minimal waiting time, average waiting time. I then put Alice here. I optimize over all cutoffs, and I'm not guaranteed to get the same average waiting time. Maybe I could do better by moving Alice around. And again, as a function of lambda, and you should really think about x. That's a parameter that will interest us more. Okay, here's the third question. Alice likes the express line. So, she made a choice for me, and I can't argue with her. So I put Alice in the express line, and painfully, by making a lot of observations, I find the optimal S after a month. And then Alice tells me she's tired of the express line, and she wants to switch. I find the optimal S. And then Alice wants to switch. Okay, so what's the new S? Should I just throw away all my computations from the last month of trial and error, or can I just somehow predict what the... Okay, here's the bad news. The bad news is for general x. You know what? Forget about general x. Let's take the simplest x. Exponential distribution. This is everybody's favorite distribution in queuing theory. Why? Because you can actually solve queues with this distribution. It doesn't matter if it exists in nature or not, then you can actually solve.
But can't you give arguments that it should arise in nature? I mean, from some...
No, I'll give you examples why not.
Right,
Have you heard of teenagers?
I have.
So when I talk to somebody on the phone, it takes me about 5 seconds. When my daughter talks to somebody on the phone, it takes 5 hours. Try modeling that with the exponential distribution.
Okay, so humans are having tail.
No,
Yeah.
but there is an argument why in some cases it is a good distribution, because it turns out if you have lots of independent processes, not necessarily Poisson processes, when you superimpose them together, in the limit you get a Poisson process.
Well, my daughter is apparently not.
I'm not saying always, but that's Pumpkin's theorem. So if you have any situation, let's say when the data network, when you have lots of independent sources superimposed together, they give an exponential distribution. So sometimes it works, sometimes.
No, sometimes it works. I'm not saying that, but it's not the reason why people in queuing theory like it. So, suppose something else worked, they would have liked this other thing. Well, here, the exponential is a disaster. I mean, you can solve all this because there's only one parameter, but your solutions are going to be completely numerical. I mean, at least I don't know how to solve any of these problems. And things could, maybe not in this situation, but similar situations actually depend on the arrival rate. And funny stuff happens. It's just not a good distribution for this type of function.
So if you look at the expected value, what does the Poisson formula gives you?
You get some ugly expression. You can solve it numerically. You can minimize it numerically, find the optimal S. But it's
How
not,
ugly is it? It depends on the purpose, but it's
it's
just
not
the second
terribly
moment that
ugly,
it's,
but still, it's not enough.
Can you prove the lack of an analytic solution?
that is an analytic solution. That's
By
why.
observation.
By observation,
alone.
okay.
I didn't try.
All right,
Okay,
fine.
but it
Fine.
doesn't look like, and I can explain to you, in a sense, the talk is explaining why it's not going to happen.
All right.
Okay.
Fine.
I'm sorry. There is an analytic solution for the general service time distribution. Of
Yeah, there is. You can write down the equations as functions of. Okay, so what David is saying, and is true. There is something called the Polaczek-Khinchin formula that allows you to actually write the optimal S as a function of the distribution. But solving it in any way other than numerical is not something that I see happening here. Okay? Yeah. The reason I chose this Q is because you can write down equations. That's why I didn't go to the shortest line or something like that, because that's hopeless. Okay? Most Qs are hopeless. If you want to say something interesting analytically, you have to stick to, you have to put the headlight and look under the headlight. So the reason I chose this thing with the cutoff, well, it's not the reason I chose it. I was looking at papers of Moore, Harfel, Balter, who introduced these kind of Qs. By the way, don't necessarily try this at home because they have a patent on this. Crovella and Harkol-Balter have patented this Q. Okay. So, I'm sorry? Yeah. Well, they're not going to sue you, but
Do they patent the entire concept of having two lines, or
Of having a cutoff.
Like, how obvious does something have to be?
Look at the patent. Go Harkol-Balter and USPTO.gov. And claim number 1 is fairly broad, definitely covers this and much more. Okay. So I was essentially trying to analyze, and the original story is not for the mini market, of course, but some supercomputer server farm, whatever. But I like the mini market. That's where I go. I never go to a supercomputing center. Nothing to do there. I really care about this problem, practically. I'll tell you at the end, I sent my students to supermarkets, so I'll tell you what happens there. Okay, poor students. Okay, so now I'm going to write down a distribution for which I can solve everything like this. It's like really, it's like bread and butter. You get this distribution, everything is analytical, life is simple. You just take your hammock as a manager and just let the mini market run itself. Okay, so here's the distribution. Okay. A nice distribution. So here's a nice distribution. Okay, we're going to define a bunch of numbers, a series of numbers, and we'll start with A1 equals to 1. Actually, let's even go back further. Forget about this. We'll start with an equation like this. Now I'm going to make some funny demands that 4a to the third plus 27b squared is not 0. And if p to the fourth divides this number, divides 4a to the third, then p to the sixth doesn't divide 27b squared. Never mind, forget about this. Just simply ignore. Ignore. Okay. Oh, but a and b, and this is really important, have to be integers. It's not going to work if they're not integers. Okay, now I'm going to define a sequence of numbers. I'm going to take a1 equals to 1. For if n and m are disjoint, are not disjoint, are have no common divisor. are
Co-prime.
co-prime, yeah. Sort of translating from Hebrew. And it's not a good translation either. So if their GCD is 1, then it's multiplicative. AN times AM is AN times M. So I have to tell you only what A of a prime power is. Okay? So I'm going to take A of P to be P minus N of P, where N of P is the number of solutions of the equation star over the field FP. Okay, you take the field with P elements, you count how many solutions. Obviously no more than P squared, but actually a lot less, at most 2P. And because this will give you something and we'll have only 2 possible solutions here, so only between 0 and 2P. And what's in the middle between 0 and 2P? It's P. So we're going to take P minus the number of solutions. Okay? And now I have to tell you what a P to the K is. Well, you can sort of repeat this trick with the field with P to the K elements, or you can use the following recursion. So if I take a to the power pk plus 1, that's AP times AP to the K minus P times A P to the K minus 1. So there's a 3-term recursion here, which actually does the work. Okay? So now I've defined for any integer the number an. Okay, one more step. So defined. Yeah, so sorry for the really poor board management. Defined an for all n greater than or equal to 1. And now I'm going to take the sequence sum of an q to the power n, and going from 1 to infinity, where q is actually a function of t. It's e to the minus 2 pi t. Okay? So I take this exponentially decaying function of t, and I take the power series, and this is a function of t. Well, this is not really, and I want this to be the density function, but it's not really good enough because it doesn't have to be positive. And in order to make something a density, I have to divide by the integral from 0 to infinity to have overall density 1. Okay? So what we're going to do is we're going to define g to be equals to f squared. That solves the positivity issue. Okay, and then we're going to take g and divide it by the integral from 0 to infinity of gt dt. And you may wonder why this integral exists. That's actually a good question. You see, there's no problem at infinity, because as t goes to infinity, this goes exponentially fast to 0, and these an's are actually polynomially bounded. So they don't really change things much. But what happens at t equals to 0? At t equals to 0, this q goes to 1, and you have integer coefficients. And now you really need God's miracle to make this converge somehow. Okay, so the miracle is true. It actually, you can do this integral. It does exist, and you can write this g. And now I'm going to tell you how to manage the mini-market with this really simple distribution. Question number 1. what is the optimal cutoff? Okay, you see this funny number, 4a to the third 27b squared? You take all the primes that divide. So, okay. So optimal S for c equals to 1. If a prime divides this delta thing, this 4a to the third plus 27b squared, you take it. Okay? Now, this thing is actually the discriminant of this cubic. Okay? Which, like, you know that in a quadratic equation, you have this thing called discriminant that you learn to take the square root when you figure things out. That tells you essentially if you have, when is the discriminant 0? The discriminant is 0 if two of the if the two roots are the same. Okay, you have a double root. Now this is the discriminant of a cubic. Over the algebraic closure of the finite field, you do have 3 solutions. If 2 of them are distinct, you take P. But if there's only one solution, so this is 2 solutions, if you have only one solution, you take P squared. And if P equals to 2 or 3, you go to Silverman's book and you can solve whatever, there's some algorithm of Tate, and then you take P to the power either 1 or 2, and then you take 1 over the square root of that, and this is your optimal S. Simple as that. Just have to take this number, factor it. Well, factoring is not that easy, but you know, any guy from the mini market can do it, I guess, for small numbers at least. And okay, so this is your optimal S. How about, does it matter where we put Alice in the express line or not? No, it doesn't. If we put Alice in the express line and optimize over S and compute the average waiting time, or put Alice in the other line, optimize over S and compute the average waiting time, we get the exact same result. And it doesn't matter on this lambda on the arrival process either. So that's easy. If it doesn't matter, let Alice choose. I mean, why argue with her? And suppose that, by the way, this funny number is called the conductor of the elliptic curve. So we take 1 over the square root of the conductor, that will be the optimal. And if Alice decides to switch on me, then the new optimum, S opt new, is 1 over the conductor times S opt old. So it took me a month to figure this out. She switched on me. I couldn't care less. I just computed again. Again, doesn't matter what the arrival rate is, anything. So really, it's a cinch to do these things. Okay? Okay, so obviously I've chosen this distribution to impress you. But it's not limited exactly to these distributions, but almost all interesting examples are of this difficulty and above. So what is happening here? Okay, I'll tell you what's happening.
Question. So if you said that t equals to 0 introduces this difficulty of evaluating the integral.
Yeah.
Let's say
Showing that it exists.
So showing that it exists, yes. If I assume that support is strictly positive, starts with epsilon onwards, that doesn't make anything. I mean, you still need to figure out that. I understand.
Yeah.
But do you sort of make?
Well, you could do from epsilon to 1 over n times epsilon over a finite interval and avoid the issue. But if you really want the entire 0 to infinity, you would need this. And this requires, at least for now, the full strength of the Taniyama-Shimura conjecture, just to prove that this integral exists. Okay? So You just have to haul in the big cannon and just shoot at the paper target. And yeah, there's a theorem of Weil that says essentially that it would be hopeless to prove it without proving Taniyama-Shimura. Almost hopeless.
So, I might be missing something, but are you getting anything out of the fact that this came from an elliptic curve as opposed to just making a distribution out of any modular form you want and then not having to use this machine?
No, it's just that with the elliptic curve, it's the easiest modular forms, which are cusp forms, not Eisenstein series or theta functions that I can write down. But I can, I can take other modular forms. They do have to be Hecke. They don't have to be Hecke, but Hecke will guarantee me what I want. And I can take other automorphic forms also for other groups, as long as they're what is known as self-dual. And I can take also some other much less exotic functions, which I'll state soon. These have another advantage, that the waiting times that you observe in queues are really interesting. You can learn a lot about the K-theory of elliptic curves and motivic homology if you just look at these numbers. But that's Bailenson conjectures and Bloch-Kato and Beert-Swinnerton-Dyer and all that kind of stuff.
The first connection between K-theory and K-Mark.
Yeah.
So what are the properties that are being...
Okay, so now let's demystify.
Yeah.
So far it's completely mysterious, and it's all really so stupid. This is a two-line computation in Calculus 1, but Riemann did it, so it's a good two-line calculation, okay? So somebody smart had to step in and do this calculation. Okay, so what's at the bottom? And I'm going to now explain. It's really simple. So it looks very mysterious, but it's actually very simple. Okay, here we go. So as David mentioned, the way you analyze these Qs is something called the Polacek-Khinchin formula. The main difficulty is writing it down correctly. And this is a formula for a single queue, just a single server, okay? And what does it say? You want to know the average waiting time. Now, actually, the average waiting time is not such a good thing to measure, because if I change my units from minutes to seconds, I just multiplied by 60. The average waiting time, if you want something a little bit unitless, then you divide the average waiting time by the average time that a customer spends at the counter. Okay, now if I change the time unit, it's going to make sense. So if you look at this thing, and you will see this equation. Wait a minute.
You want one of them with the square on the outside or something? Or?
Yeah, definitely. Thanks. And I don't want this lambda here. I want rho, where rho is lambda times E of x. Never mind. This is what is called the utilization. What portion of the time is the server busy serving a request? No, I'm not done yet. Yeah, you're right. And you also need this 2 times 1 minus rho thing. Okay. You see, as the utilization approaches 100%, the average time you wait just explodes. It means that the system has reached its full load. Okay.
Sorry, what's lambda?
Lambda is the arrival rate of customers, like three an hour.
All right, good.
Okay. And if I take lambda and multiply it by the average of the time that you spend in the server, this tells you what percentage of the time the server is busy.
Yep.
Okay? So this is the equation. Now, I'm going to do something that looks really, really stupid. Okay? What I'm going to do, if I have this function ex to the power k, I'm going to write it as Lx at the point k minus 1. Okay? Let's work with the definition. What is e to the x to the power k? If my density function is f, then it's just the integral of t to the power k, f of t dt from 0 to infinity. Okay? Now I'm going to write what is L of x at the point s. So instead of calling it k, I'm going to change the variable to s. This is crucial. This was the main obstacle for progress on this problem for a long time. Okay? Lx of s is the integral of t to the power s f of t dt over t. The reason I chose dt over t is that dt over t is the Haar measure for the multiplicative group of the positive reals, and this is a character for the positive. This is like a Fourier transform. And it's like a Fourier transform just called a Mellin transform. This is the same kind of stuff. What?
The Lx k plus 1 then?
No, because here I have s minus 1.
S minus?
Because the
Right,
dt
so
over t.
matched with t to the k?
So k equals s minus 1. Yeah, you're right. Yeah, sorry. Sorry for that. You're right. Yeah. Okay. So, let's ignore this part because this part has essentially little to do somehow with the distribution. But let's look at what is written here. What is written here is upstairs I have Lx at the point 3 divided by Lx at the point 1 squared. Okay? Now here's a really amazing trick.
At point 2.
Yeah, jet lag. Okay, I'll blame it on jet lag. Now here's the really nice trick. If you have a density function, what is Lx of 1? It's the integral from 0 to infinity of the density. So that's 1. So I'm going to just put here an Lx of 1. Just for fun, okay? I just multiplied by 1. I'm allowed to do that, okay? So essentially, the Polaczek-Hintschen formula, written in terms of the Mellin transform, and nobody's written it that way in 80 years, is this. Okay, I didn't do anything. I just wrote it this way. Now, why would I write it this way? Because Mellin transforms play a really important role in number theory. And this is what I'm going to try to explain in the last 15 minutes so you see where this magic comes from. So in number theory, and let's forget about the management problem. We decided that it's easy in these cases.
And by Mellin transform, you mean the transform of the function f?
Of the density function, of the job size, of the time at the server. Yes. Okay, so here's what Riemann was up to. So Riemann wrote this function, well, not Riemann, Euler had this function, sigma n to the power minus s, n equals 1 to infinity. And this is the zeta function, okay? And this converges if the real part of s is greater than 1. So the first order of business for Riemann, and Riemann wrote just one paper on number theory, 9 pages. It's a masterpiece. His first order of, he wanted a formula for the number of primes up to n. So he wrote down this, he wrote down Euler's function essentially. And then he wants to extend it. He wants to find a definition that will be what is known as analytically continue this, so not just any way of continuing it, but in a nice way, to the entire complex plane, or almost the entire complex plane. And in addition, he sort of wanted an equation of this type. It doesn't really equal, but you have to add some stuff. But he wanted something that looks like that. Okay? Now, how do you get that? So, Riemann remembered that his pal Jacobi, about 30 years before, introduced this theta function, which is the sum over all the integers of q to the power n squared, where q is the same. It's actually not e to the minus 2 pi t, it's e to the minus pi t. Never mind. Well, it's almost what we had before. And what Jacobi was able to show is that the theta function satisfies this functional equation. Theta at the point t equals theta at the point 1 over t times t to the power minus a half. Okay? Now, in general, you might be interested, if you, more generally, you may want to look at functions which satisfy this type of functional equation. Because what we're going to do is going to work more generally somehow in this setting. So suppose you have something that satisfies this or this, and suppose that you look at the Mellin transform, at the moments, at the complex moments of this function. Okay? Then this functional equation will translate into, again, I'm going to do almost, this kind of functional equation, which is what Riemann wanted. And what he showed that it's not the theta function, you have to massage it a little bit, you have to take out some terms so things will converge, but if you do the math, the Mellin transform of the theta function is almost the zeta function. Okay, and it actually puts in exactly the correct terms, which is the gamma function, and everybody's happy. Okay? So, Riemann got a 2-for-1 deal because he used the theta function to get this thing, and this immediately also gives you analytic continuation.
So
Why?
what is the general principle here that if you have t on one side and 1 over t on the other side, and you take the Mellin transform, it will become s and 1 minus s.
Yes. And moreover, you know that this converges very rapidly to 0, the q, at t goes to infinity. But if you have the functional equation, and you take a small t, you get here a big T, and this is just polynomial, so you get exponential decay to 0. You get fantastic cancellation, which is hard, which is essentially possible to prove otherwise. And that allows you to take the integrals, to take the moments. They will always converge. So you get analytic continuation, and the poles come from some, things that come in the middle.
I still don't understand. What are you using here besides that the moments are easy to compute? Besides the...
No, I'm getting to the point.
Okay.
I still have 10 minutes. I'll try to get to the point in 10 minutes. Now, this was for minus a half, and don't ask me how this got into 1. It should have been like a half, but there's a lot of cheating going on. But in general, if you have something like that, and you take the Mellin transform, you will get an S paired with K minus S. This is the functional equation. Okay? Here you got a 1 because it's the 2S and not S, but no. This is what actually happens. Okay? Now, let's take this functional equation and apply it with K equals to 4 to the Pelagic-Khinchin formula. 1 becomes 3. 3 is 4 minus 1. 3 becomes 1. 2 stays in the same spot. So the Pelagic-Khinchin formula is symmetric with respect to the functional equation which is typical of L functions. L functions in number theory usually come from counting solutions over finite fields of polynomial equations. The zeta function is just the really difficult equation x equals to 0 in one variable. Just has one solution over any finite field. That's why all these coefficients here, usually you would have an an, and they're all 1 here. Now, it's more complicated, of course. You use some Lifshitz trace formula. You want to take part of the solution. Never mind. But in principle, that's what happens. And every time you count solutions over finite fields, you're supposed to get something like this. Nobody knows how to prove that except the Riemann function and some other cases, and the Taniyama-Shimura that tells you that counting these solution counts satisfy this, come from some, they're the Mellin transforms of something that satisfies this type of functional equation. That gives you analytic continuation for these functions, which was not known before. In particular, it gives you a value at the point 1, which is the subject of Bird-Swinnerton-Dyer conjecture, which is worth $1 million in a job anywhere you want if you can prove. And so until Wiles's work, Tate said the Bird-Swinnerton-Dyer conjecture relates something which is not known to exist to something which is not known to be finite, because the other side is supposed to compute it contains some group that nobody knows is finite. But at least now we know that it exists. Okay? And this is very typical. This kind of anything, you will not be able to call yourself an L function unless you satisfy this. And if you happen to have weight 4, you're symmetric with respect to the Polaczek-Hintschen formula, and that's the magic. You still have to do just a tiny bit of work, but that's essentially the magic. Now, if our target function was not average waiting time, but we tried to find the best cutoff for the average of waiting time divided by job size, this is called slowdown, where the penalty for a small job waiting is bigger, then you would get an expression which is a little bit different from this. It will look something like L minus 1, L2 divided by L0, L1, which has a weight 3 symmetry. And if you want higher moments of the waiting time, you'll get other weights, other k's involved. So it turns out that the analysis of these Q's depends on what you try to optimize, which has a certain weight of symmetry. This is called, the K is called the weight. And you have, the distribution might have a weight, and when you pair this against that, you will understand very well what will happen with the Q. Something like that. It's sort of like, it's all representation theory in some sense. These K's come from representation theory.
Wait, so I'm confused, because even without any of this L function stuff, that expression on the right-hand side of the Polaczek-Hintschen formula, over there, right? Like it doesn't look that like it would be that hard to minimize as a function of lambda. It is.
Well, if you have two hosts and you have a cutoff, you get an integral from 0 to s of some ugly function.
I see. I see. Because you just showed it for one.
And then you could solve it and definitely solve it, but it would be unenlightening. Okay, if you're looking for something interesting, this would not be interesting.
Okay. All right.
Okay, there's nothing interesting there. Okay, what other things that satisfy this kind of equation exist with k equals to 4 apart from this really exotic example? Here's another example. F of t is what is known as a bounded Peridot. F of t is, well, approximately t minus 2, but where you cut off. You take it 1 up to some big number, and look at the finite range, so because you do want to have a second moment. You won't if you take from 0 to infinity. And in general, you can put here a t to the minus alpha minus 1. And then there is this, if you know Terry Tao's blog, there's on Peridot Law, Benford's Law, Zipf's Law. This is Peridot Law. And he sort of states there that it has been observed many times in real systems that you have alpha equals to 1. Okay? Alpha equals 1.1, alpha equals... And there's no conceptual explanation. Well, here I can provide a really beautiful semi-mathematical explanation. It turns out that when you take alpha equals to 1, which is exactly putting here at -2, that's self-dual of weight 4. And it turns out to be the absolutely worst possible distribution among all distributions in the world for waiting time. So this is what Tao was asking, gets a solution from Murphy's Law, which is a well-known law that holds in general. And here we have just one more example of Murphy's Law.
Isn't that sort of an opposite explanation that you would expect that any reasonable system will sort of evolve towards the best waiting time rather than the
You're
worst?
kidding me. Have you ever waited for files on the internet?
I'm not saying that's a reasonable
Evolve into the best possible? I'm in the high-tech industry 18 years. It doesn't work that way. Actually, you want to increase the number of bugs so they can't fire you. If you have a really good working system, they'll dispose of you. And that's at least my experience. Anytime I did a good job, they stopped the consulting after a few weeks. They didn't need me anymore. Yeah, exactly. You want to put a good number of bugs in the system.
This is assuming that, say, the cashiers can sort of control the advertising for the mini mart so that they can attract the customers who take the longest to serve.
Nobody really knows how Murphy's Law works. It just, this is God's work. I mean, don't wander into the mysterious. There's the saying in Hebrew. Don't go there. Okay. So, okay, I think this is a good time to stop before we really get carried away with all kinds of nonsense. There are some other example log normal, who cares? You can characterize log normals using these kind of functional equations. They satisfy them for any n, so they're... And you can characterize the number theoretic ones. This is Weiss or generally Piatetsky, Shapiro, all these converse theorems. That's what they do. Okay, so I'll stop here.
Any more questions?
So are these elliptic curve-based distributions
Oh,
good for anything else?
Okay, so...
I mean, it sounds like if we want a nice expression for waiting time, you could have, just told us just take the.
There are some other cues where they work well, but and so the question is, first of all, are there? You see, I cheated. I took here a square, which is a real no-no in number theory. It's like I killed it. It's not Hecke anymore, and people will get really mad at me if they see that. So what you want is a real 4 form. Never mind. But suppose I didn't take the square. All I would have to do is invent change my target function so it will be symmetric with respect to weight 2. And I can do that. It's easy. So you first choose what you want, and then you choose your target function, so the math will work out nicely, in the spirit of queuing theory. And then, for example, the question is, how many of these functions, if I don't take the square, are they positive? Are they distributions? Okay? And Taniyama-Shimura tells you that you can normalize them. And the normalizing constant will be the Bird-Swinnerton-Dyer thing. So that's a very good question, and I emailed Peter Sarnak, and he said that he usually doesn't bother with these amateur questions. He was actually working on something similar. And so he got interested in that. And so the latest word you can find in my website, an 18-page letter that he wrote me. There are plenty of examples. There are hundreds of thousands of elliptic curves where this thing is positive, but they become less and less likely. And the question is, are there infinitely many or not? And that turns out to be extremely difficult and deep question. In some cases where instead of taking n to infinity and fixing k, you take k to infinity and fix n, that's what is known as the quantum unique ergodicity or high energy regime. And there, Sarnak and Gauss and Reznikov have recently proven that there are actually only finitely many examples. But the arguments won't work for these. So these are really difficult questions. Yes.
So just to be clear, so the set of examples that you have for which you can do these exact calculations of what S are, it's just a finite set of examples, or you have a way to produce?
No, I can produce infinitely many.
Are they dense in the
I can produce, again, it depends how much cheating you want to do. You can always use Eisenstein series instead of cusp forms, but then you have to do, like in the Peridot case, you have to cut them off. You can do, for these, it's not clear whether it's an infinite number of examples or not. There are plenty, these are ubiquitous. Solving this differential equation, functional equation is like being an even or odd function, essentially. You can choose t to be anything between 1 and square root of n, 1 over square root of n, and then 1 over square root of n to infinity. The question is, if you just choose a random function, it's not going to be analytic, it's not going to be nice, it's not going to be anything. There are a lot of even functions or odd functions, but most of them are not like sine and cosine, which are everybody's favorite example. Okay? So these are really nice examples.
If I had a distribution and I asked you, could you
Yes.
come up with one?
Then you would have a regression problem, which would be nonlinear, and I'm actually trying to sort of semi-solve it because I want to put this into the list of function properties that are used by this guy at the Technion, Avi Mandelbaum, which traces call center data and hospital and whatever. And if I can find an elliptic curve in a call center, hopefully not in a hospital, it could be dangerous, then I think that would be cool. Oh, log normal is in this family, so, and that is ubiquitous when you do real modeling. Yeah.
But is there a way to approximate I have my favorite distribution,
Yeah.
you come up with
That's a
sequence.
good question, and I'm trying to find a student who will do that as his master's thesis, because it's an infinite dimensional nonlinear kind of thing. It's semi-linear, it has a cone structure.
There
And
is some stability in what S is based on, if you vary the distribution of X a little bit, S will only vary a small amount.
yeah. That would definitely be true.
So, in this expression on the far left, I mean, these were like both symmetric about some axis of symmetry, right? But,
Yeah.
I mean, was that just like a miraculous coincidence in these two cases, or were?
Pretty
if you
much.
write down like some other problem, it might not be symmetric.
Yeah, so if I take like higher moments, so I want to optimize fairness, so I don't care how much they wait as long as they wait equally long.
Yeah.
So I would get some expression. It will have a leading term that would be symmetric, and then I would get a lot of garbage, which I just hope will be negligible. Sometimes it is, sometimes it isn't, but it actually in a good, if it's heavy-tailed, it usually will be fairly negligible because the highest moments outweigh strongly all lower moments in heavy-tailed.
And that's actually good for you?
Yeah, that would mean it's more symmetric. So I have something which is really symmetric and then garbage that I just want to sweep under the rug or something. So, but then again, I'm not really trying to be, I wouldn't consider this to be one of my practical works. I do a lot of practical works. As I said, I have more patents than papers actually, but this is not something I'm going to make money on. And there's a patent. I mean, I'm definitely not going to make money. Yes.
You are in a heavy traffic, then there's again approximate formula, which involves the second moment of the interarrival times now. Could you do something there?
Write it down to me. I'll write it in the Mellon transform. Let's see what happens. Yeah, this heavy traffic, everybody tells me all the time, and somehow it's like You know, it's like a black hole for me. I mean,
No.
I hear heavy traffic, I close my
case,
eyes.
it's very,
and
if
shut down.
lambda is close, if lambda is close to the expectation of x, then it's
Yeah.
just the second moment of interval plus second moment of service times divided by something like twice 1 minute. So it's a
Yes.
very explicit form.
Oh. Okay, so
Very
second
explicit.
moment of, but you see here, the second moment of interarrival is not good for me because that's exponential. And it will not,
No, I'm saying it's not exponential. But what do you mean?
because I'm taking Poisson arrivals.
No, but what I'm saying is, suppose it's not Poisson arrival, any arrival process.
But then I don't have Polaczek-Hinge. Oh,
But-
but I do have heavy traffic. I do have,
Right.
yeah. So actually, if you have an arrival process with an Eisenstein series or something, it will be good, yeah. I never thought about that. Okay. Arrivals are Hecke and, yeah, okay. That's a good thought. Yeah, I'll get something. The theory will work the same. It's very formal algebraic theory. There's sort of no content here, so. It's all observations, but I think it's cool observations. I don't know. I'm happy about it.
Let's thank the speaker again.